Hey everybody. So this is a research paper that caught my eye, and I have dissected it at this point, and I can actually make some innovations in this area with regards towards what they're working on with this. So let's talk about this research paper, what they're doing, what they're innovating on, and what the innovations that I can add on top of this. And then so this research paper is called Fast and Simplex 2-Simplicial Attention in Triton. And then so the simplest way to break down this research paper is to break down the individual concepts within this research paper and then explore and explain exactly what's going on here and how it's working and what they're solving. So the problem that they're trying to solve, like why all of this exists, is because of this, right? Quadratic complexity. And then this is it, the equation, O times n squared, n to the power of 2, right? And is the input time series length. It's a computational bottleneck. And then so what happens here is essentially that you have a quadratic scaling problem when it comes to the attention mechanism. And the reason why you have this equation, this O(n)(2) equation, is because of the attention matrix, because attention is broken down into a two-dimensional matrix, like what we're seeing here, right? And what we're seeing like in all of these images, like here's the, this base one, like A is the base here, and then so here's the base. We can see here essentially what we're looking at are two-dimensional matrices, right? And then so the bigger that this matrix goes, like every row that you add, it increases complexity by O(n) squared, right? And then that's kind of the, or O(n) to the power 2. And that's the equation within that. And then nothing changes that specific equation whatsoever, right? Like the only thing that we can do to that equation is like these sparse attention calculations. And then so like sparse transformers, where we essentially like remove some of the like layers of the attention matrix and the attention mechanism. But the problem is when you're dealing with like words, like how exactly and what is the best way to make it sparse. So let's take a phrase, right? Like, how are you doing? So this is then gets made into this matrix, right? And then so how are you doing? It gets put into this 2D matrix that we're looking at here on the right-hand side. So what is the best way to make this sparse? Like, how you doing? Like, we could remove the R, right? So then, like, I guess that's what sparse attention does and attempts to do, right? But it's hard when we're dealing with language within that. And then so that's why you run into issues with sparse attention overall, is because it's taken in context. And I'll explain this and I'll show this out and I prove this out a bit further when I dive into kind of the notebook here, right? But then so the standard like kind of way to solve for this, like there's the two ways that have been invented to solve for this are sparse attention, which I've mentioned just now, right? Which is to essentially like try to remove calculations that the model has to make and make it more sparse. Or the second way is this linear time attention, right? And then linear time attention, you would be familiar with if you're familiar with like Mamba models. Like anything that is RNN based, that's linear attention. And then so like the thing to me with linear attention, just flat out, is that like it's great within the context window. So let's say that the model is a 200,000 token context window. It's amazing as long as the model is operating within that, and then it just falls off a cliff. Like it's not the same. There's something like lacking within that overall compared to transformers architecture overall. That's kind of, I mean, just the simplest bottom line way that I can put it. Why there's a lot of buzz around Mamba models, things like that. Why it hasn't maintained forward and continues, even though like progress continues with Mamba research, etc., is like flat out because of that in my mind, right? It's just there's something lacking within it. It's not the same. And then so up until this point, these are all of the methods that have been invented to solve this problem here, right? So again, everything that we're talking about is very specifically because of this problem. And there's been no way invented that directly addresses this problem. All we can do is work around this problem, right? And then this problem comes up for scaling. And then so within this particular research paper, this research paper is all about inherently LLM model scaling, right? And that's kind of what they show. So their first kind of thing that they outline within the paper is like this whole like quadratic attention problem, and then how it works, and then like outside of that we have neural scaling laws, so that like if the world were perfect, if we had access to unlimited data, then we could scale unlimited, right? But the problem is that we don't have unlimited data, and then so our current models utilize the two, like essentially this attention matrix that we're looking at here. And then so what they do is they like invent this two-simplicial transformer, which leads into determinant-based trilinear forms. And then so the rest of it is just breaking down their model, exactly what it does, etc. So and benchmarking it out, showing that this is actually really cool, does well. So what exactly does this do, right? So again, going back to your typical attention matrix, a matrix is like this, right? A two-dimensional matrix. And then we can see here, so we have words, right? So the agreement on the European Economic Area was signed in August 1992. And then this is the what the attention matrix looks like for that particular sentence, right? And then, so it's a two-dimensional representation. With attention tensors, it looks something more like this, or like this, or like this, which is actually, if you're looking at these two things, your first instinct would be that, so this compared to this is far more complex than this, right? And then you would be very correct. Like this architecture, significantly more complex than this architecture. And then if you're paying attention and you're thinking linearly with regards towards these things, then your next assumption would be, well, that's backwards compared to what we're looking at with kind of these other methods, like this, we'll call it the Mamba method, sparse attention, etc., because they're trying to simplify this, whereas this is getting more complex than that. So how exactly is this better if it's actually increasing the complexity? And it very much is, right? So instead of ON2, this equation, what this is doing flat out is ON3, like flat out. Like, so it is significantly increasing the quadratic complexity. It's no longer quadratic, it's ON3, it's cubic. And then so far more. But so then how is this better? How is it, like, what are they doing? What's the big breakthrough then within that, right? So then what they do within this is, so you have this model, but then they also add a sliding window onto this. And then so the sliding window moves across, and then it's essentially for attention models and attention mechanisms, which is interesting because like 2 years ago, I was actually like working on, I'll show it to you, like this exact thing, right? And then let's go here. I find it interesting, right? Because like some people were like, they don't understand where I get like my math from, or how exactly I come at these mathematical things, or you know, they try to question things around that. But so here we go, October 23rd, 2023. This is Cadane's sliding window, right? And then so this is a sliding window very specifically for the attention mechanism. And like, this is not the same as the meta sliding window, right? But it's the same underlying concept. So like they're increasing the complexity from ON2 to ON3, but then their solution to that is a sliding window concept, not Cadane's sliding window, but they invent their own sliding window for this. Like they very specifically, this secondary part that they're doing, like this second algorithm is like their own kernel algorithm that is doing the same thing that I'm doing with this, right, for the attention mechanism. And then what they're building out in this instance is, or for here, for their attention tensor, is that sliding window for their attention tensor overall, right? And then so at the top, I mentioned that I have my own kind of research into this that I can add, which would be a significant breakthrough over what like all of these methods are looking at here. And then so my method, very simplistically, is just to add swarm algorithms to the attention mechanism itself. So swarm sparse attention is what I call this overall. And then so essentially, the setup is very simplistic, right? So I have a teacher model that I have that generates the attention matrix. And then so we get whatever the attention matrix is that the teacher model gets, and then we like remove it, make it sparse, add some noise to it, and then the student model tries to guess what the teacher model's attention matrix is. So like that's what the student's job is in this instance. And then so essentially I go through and then I do different tests on this, right? And then so in this first test that we're looking at here, and I did a bunch of tests before this, but this is just kind of where my tests like came out at the end. So in this first instance, we're testing at 90% sparsity. And then I have a random mask test. So essentially what this is doing is just like you're like most base sparse attention possible. Just, you know, essentially like let's go from there and then try to recreate from sparse attention. This oracle mask is essentially like the top K. So like what's the models, the student model's best predicted, like, and the best outcome that it can come up with. And then the last one here is in this first instance, I'm just doing particle swarm optimization, which is like the most basic form of swarm algorithm that you can do in this instance. I just like slap it in, see what happens, and then with just PSO swarm algorithms, it outperforms anything else that I tried, right? So PSO, discovered mask. This method is the decisive winner by treating the problem as a global optimization task. The swarm algorithm found a combination of attention connections that preserved the final output far better than the other methods. This shows that the best sparse mask isn't just the sum of the strongest individual parts, but a holistic pattern where connections work together. And kind of what I want to point out within this, and it's better illustrated with one of the later tests that I have here, this one here. So let's look at this and then I'll go back up. But so again, like the model outputs these attention masks like this, right? And then so this is, pretend this is words, this is a sentence, and then overall, right? And then we're trying to, like, rather than the sentence overall, the model's trying to predict this. It doesn't care what the sentence is. This is what it cares about, right? Like essentially like this QR code, basically. Like if you get the QR code right, the model will know exactly what the sentence is. And then that's kind of how the models operate and what they're doing within this, right? They're just reading this QR code. And then our job is to get the best QR code or the best representation of this QR code possible that we can do. And then so what sparse attention does is, let's just focus on the left, right? And then let's say that this left one is our QR code that we want to have the model do. What sparse attention does is it just removes 90% of this QR code, and then it has the model reconstruct it. But then if you do that, the model's probably going to reconstruct it like something here on the right, because it's not taking it, like the model doesn't reconstruct based off of the full picture, the full snapshot, right? It's just like, okay, here's this one pixel here, what's the pixel next to it, this, and it's kind of like trying to go outwards, right? But it's not taking in like the whole entire thing. And then so with swarm algorithms, it just it's the opposite. That's what it does, right? The swarm algorithm can act like a camera, take that snapshot picture of what this attention, what this looks like before it actually does anything, and then it's just trying to match that picture, and then that picture, and then trying to match that picture is a super fast process, like computationally, right? And then so when we do that, like the very first test that I showed you was at 90% sparsity, and then at 50% sparsity, we still have it outclassing, right? So it's still the best method, and this is just PSO swarm optimization. You can see 0.92 seconds for it to complete, like less than a second for the PSO optimization to go through. And then in this next test, I'm like, okay, let's actually input, and we'll go for my swarm clean optimization, and then we'll see if I can improve that even more. And then so So we had basically like a 1% increase between Oracle and PSO. For SQO, we get 4% increase, 4.5% increase. So significant increase going from PSO to SQO. So significant increase going from just like top K-score and random masking to PSO and swarm optimization, but then going from PSO to SQO, massive improvement there, right? But then I'm like, okay, can I improve this SQO algorithm even further? And then so I get it up to 69%, basically 68.94. So like a significant jump, almost 7% or 7% point improvement over the Oracle Top K with regards towards the performance there. So massive improvement overall, and then with like regards towards all of the normal sparse attention mechanisms and the way that people are calculating these things just by incorporating swarm algorithms into this. And then so that's just my overall contribution to this, and highlight within this as to like the advantage that you can have by taking and understanding how these algorithms fit together and work together overall. And then just once I do that and start picking apart and I look at, what's going on here, what's going on here with regards towards all of this, then I was like, what would solve all this better rather than going to the ON3 complexity and doing this? I do think that this is a full method, and I think you could combine like that ON, like the research from this paper with this final output here, and you might be able to get something super cool. I didn't go that far, right? I'm just sticking with the matrices. But overall, like I think that like if I was to choose a method out of these three, this seems to me to be the better overall method. This method overall is sacrificing computational performance for increased score here. But like when we go to their own benchmarks here on this, like I don't think that they're beating out the model that I'm showcasing here, and if they are, it's not by very much, right? Yeah, like I'm significantly beating their improvements on their benchmarks here with their experiments and results, right? So out of the three methods, this is the better method, a far better method here overall, and here's the benchmark results to prove it. So I'll leave a link to all of this here for you so you can play around with this research paper as well as this collab notebook. And if you like this type of content, please like and subscribe. Thank you very much.